Hey, welcome to the last section of this video course, Statistical Programming and Linear Regression. In the previous section, we explored about input, output, physical format, and logical layout. In this section, we will learn to use the built-in statistics library and find the average of values in a counter. We will then compute the coefficient of a correlation, regression parameters, and an autocorrelation. We will also have a look at confirming that the data is random, that is, the null hypothesis, locating outliers, and analyzing how many variables in one pass. Let's move on to the first video of this section, where we'll be using the built-in statistics library. In this video, we will compute the mean, median, mode using the Statistics and Collections module. Data analysis and statistical processing are very important applications for sophisticated, modern programming languages. The subject area is vast. The Python ecosystem includes a number of add-on packages that provide sophisticated data exploration, analysis, and decision-making features. A great deal of exploratory data analysis, that is, EDA, involves getting a summary of the data. There are several kinds of summary that might be interesting, like these three. First, central tendency. Values such as the mean, mode, and median can characterize the center of a set of data. The next is extrema. The minimum and maximum are as important as the central measures of some data. And the third one is variance. The variance and standard deviation are used to describe the dispersal of the data. A large variance means the data is widely distributed. A small variance means the data clusters tightly around the central value. How can we get basic descriptive statistics in Python? Let's get the answer to this question. Now we move on to the Python command shell. Open the code and click on Run. We'll look at some simple data that can be used for statistical analysis. We've been given a file of raw data called anscombe.json. It's a JSON document that has 4 series of XY pairs. Let's read this data. So, let me first import the path module and JSON. We also import ordered dict. Here we've defined the path to the data file. We can then use the path object and read the text from this file. This text is used by json.loads function to build a Python object from the JSON data. We've included an object _pairs_hook so that this function will build the JSON using the orderedDict class instead of the default dict class. This will preserve the original order of the items in the source document. Now let's examine the data. For this, you need to run these commands. The overall JSON document is a sequence of subdocuments with keys such as first and second. Each subdocument has 2 fields, series and data. Within the data value, there is a list of observations that we want to characterize. Each observation has a pair of values. This is what the data looks like. This is a list of dict structure, typical of JSON documents. Each dict has a series name with a key series and a sequence of data values with a key data. The list within data is a sequence of items, and each item has an X and a Y value. Now to find a specific series in this data structure. We have a number of choices. The first choice we have is a for-if return statement sequence. Let's implement it. This for statement examines each series in the sequence of values. The series is a dictionary with a key of series that has the series name. The if statement compares the series name with the target name and returns the first match. This will return none for an unknown series name. Next, we access the data using the getSeries method and the length method. We can use a filter that finds all matches from which the first is selected. Let's do it. The filter function examines each series in the sequence of values. The series is a dictionary with a key of series that has the series name. The name_match lambda object will compare the name key of the series with the target name and return all of the matches. This is used to build a list object. If each key is unique, The first item is the only item. This will raise an index error exception for an unknown series name. Now we again access the data. Let's use a generator expression that, similar to the filter, finds all matches. We pick the first from the resulting sequence. This generator expression examines each series in the series of values. The series is a dictionary with a key of series that has the series name instead of a lambda object or function. The expression sSeries is equal to series name will compare the name key of the series with the target's name and pass all of the matches. This is used to build a list object, and the first item from the list is returned. This will raise an index error exception for an unknown series name. Now let's again access the data. Once we've picked a series from the data, we'll also need to pick a variable from the series. This can be done with a generator function or a generator expression. A series dictionary has a data key with the sequence of data values. Each data value is a dictionary with two keys, x and y. This data_iter function will pick one of those variables from each dictionary in the data. This function will generate a sequence of values that can be used for detailed analysis. In this case, we picked the series' fourth value. From that series, we picked the x variable from each observation. The length of the resulting list shows us that there were 11 observations in this series. Next, to compute the mean and median, use the statistics module and write these commands. So, we define the samples, mean, and the median and use the print function to display the values. This uses getSeries and getIter to select sample values from the one variable of a given series. The mean and median functions handled this task nicely. There are several variations on the median calculation that are available. To compute mode, we need to use the collections module. So, type these commands. This uses getSeries and dataIter to select sample values from one variable of a given series. The counter object does this job very elegantly. We actually get a complete frequency histogram from this operation. The results of the most common method show both the value and the number of times it occurred. We can also use the mode function in the statistics module. This function has the advantage of raising an exception when there is no obvious mode. This has the disadvantage of not providing any additional information to help locate multimodal data. The extrema are computed with the built-in min and max functions. Let's compute this. We first define the series, samples, least, and most. This uses getSeries and dataIter to select sample values from one variable of a given series. The built-in max and min functions provide the values for the extrema. Now to compute variance and standard deviation. We can also use the statistics module. We use the same commands here too, along with the defining variance and standard deviation. This uses getSeries and dataIter to select sample values from one variable of a given series. The statistics module provides the variance and standard deviation functions that compute the statistical measures of interest. These functions are generally first-class parts of the Python standard library. We've looked in three places for useful functions. The min and max functions are built in. The collections module has the counter class, which can create a frequency histogram. We can get the mode from this. The statistics module has mean, median, mode, variance, and stdev, which provide a variety of statistical measures. Note that the dataIter is a generator function. We can only use the results of this generator once. If we want to compute a single statistical summary value, that will work nicely. When we want to compute more than one value, we need to capture the result of the generator in a collection object. In these examples, we've used data_iter to build a list object so that we can process it more than once. Awesome! In this video, we have learned to use built-in statistics library.